In this problem, we are finding the extrema and the inflection points of a transcendental function. And just as a reminder, extrema, those are the local maxima and minima of a function. They're also asking us on which intervals the function is increasing or decreasing, and then the max and the min, and also the intervals on which it's concave up and concave down, and then the inflection point. So we've got to find all of that stuff. To find the extreme of the local maxima and minima, and to find the places where the slope might be changing, we want to look both for, well, for all the critical points. So both for places where the first derivative is undefined, and also where the first derivative is zero. To find the inflection points, we need the second derivative, and we'll look at where the second derivative is zero. So let's start deriving. That's our first job. We've got a transcendental function, so one of these functions with logarithms or exponentials. So that'll be a little bit of a challenge. It looks like we're going to have to apply the chain rule here, but this one shouldn't be too difficult. So I'm going to do some deriving over here. So f prime of x is going to be 1, and let's see, let's call u x squared plus 5 in our chain rule. So this is going to be 3 times the natural log of u. So well, let's rewrite it that way. So x plus 3 times the natural log of u, and u equals that. Now, when we take the derivative of the natural log of u, it's going to be 1 over u. That 3 is going to stay on top. So we're going to have a 3 on top of the fraction and a u on the bottom, and then we have to multiply it by u prime. So the derivative of u is just 2x, that 5 disappears. So we can fill all this out. F prime of x equals 1 plus 3 over, and let's put u back in here, x squared plus 5, and then times 2x. Okay, so we have 1 plus, multiplying here, 6x over x squared plus 5. That'll work, except I think I want to actually make this one quotient. So what I'm going to do is change the 1 into x squared plus 5 over x squared plus 5 and add that all together. And we're going to get x squared plus 6x plus 5. Oh yeah, that was the right thing to do, over x squared plus 5, a little fraction f there. Now, when we're looking for the critical points, I don't think there's any place this can be undefined. It's always going to be positive in the denominator. On the top, we can find where it's equal to 0 if we set this equal to 0, and we can do that by factoring and setting each of the factors to 0. So this is a pretty easy factor. It's just x plus 5 times x plus 1. And if we set those equal to 0, we get x equals -1 and x equals -5. So probably local min, local max, well, certainly a local min or local max at those points. Let's find our intervals on which it's increasing or decreasing. So we're actually going to test this function at points in each of these areas, each of these intervals. We could start over here and throw in 0 because that's pretty easy. If I put in 0 into this derivative, I get 5 over 5. So that's positive there. If I put in, let's say, -2, I'm going to get 4 minus 12 plus 5. That's going to be negative on the top. The bottom's always going to be positive. So negative over positive is negative. And then when I get down to, let's say, -6, so that's going to be 36. Minus 36 plus 5. That's going to be positive on the top. So that's going to make the whole thing positive. So we can see that this function is rising until it gets to -5 and then falling. So this is a local max. And then it's falling until it gets to -1, and then it starts rising again. So this is a local min. Okay, so I think we can start filling in some of our answers here. The intervals on which it's increasing, there are 2 of those. So it's from -infinity up to -5. And then we'll put that union sign there. It's from -1 out to infinity. So that's where it's increasing. And where it's decreasing is just from -5 to -1. Okay. Now the local maximum points. We have the x values, but they want an ordered pair here. So we got -5 comma something, and -1, comma something. To figure out what that is, we got to put it back in the original function. If I put -5 in here, I'm going to get 25 plus 5, that's 30. So I'm going to get actually -5 plus 3 times the natural log of 30. And I think they want, yeah, they don't want decimal approximation. So I'm not going to try to take that natural log with my calculator. We'll leave it like this, and it's an exact answer. We'll do the same thing with -1. It's going to be mostly the same, except we're going to get a natural log of 6 and a -1 there. So this is -1 plus 3 times the natural log of 6. Okay, so those are our extrema. Let's do the next step. Let's find the second derivative so we can figure out where it's concave up and concave down. I think what I'm going to do is take this form here. Well, actually 1 plus 6x over x squared plus 5, rather than this one, because here the 1's going to disappear when I take the derivative of that. So this is a slightly easier quotient rule problem. So let's try this. So I know this part's going to go away. Work on f double prime of x here. So it's going to be quotient rule applied to this part. And I always remember the quotient rule is low d high times high d low over low squared. Low is x squared plus 5. D high is the derivative of the top here. That's just 6 minus high d low, so 6x. And the derivative of the bottom here is just going to be 2x. And all that's over low squared, x squared plus 5 squared. And we can do a little bit of simplification here. So that's 6x squared plus 5, plus 30 minus 12 x squared. So we're going to have, well, let's write it like 30 minus 6x squared all over x squared plus 5 quantity squared. Okay, so looking for places where the concavity might change. I don't think this is going to be undefined anywhere. Again, that bottom is always going to be positive, but we can certainly look for the zeros where the top is 0. So this would be x squared equals 5. So I maybe skipped a step there. If you take this and set it equal to 0, just this top portion, and then you subtract 30 from both sides and divide by -6, you get x squared equals 5. And then we're going to take the square root of both sides, and we're going to positive and negative square root of 5. So those are our inflection points. And let's we want to find the intervals on which it's concave up and concave down. So I'm going to make a similar chart here. And we're going to plug these values in. Now the square root of 5 is a little bit more than 2. So we could put in a -3 in our second derivative, and we could put in a 0, and you can put in a +3. So let's try that. Let's put in 0 first. So 30 minus 0 over 25, that's going to be positive. So that's concave up. Oops, that was 0. So that's concave up there. Let's put in a +3. So 9 times 6, 30 minus 54 over bottom is always going to be positive. So this is negative on top. So that's concave down. And then, it's going to be the same thing for negative square root of, -3, because that -3 gets squared right away. So we're going to have concave down here. Okay, so let's go back now, all the way back. And we've got inflection points or intervals on which is concave up. The concave up is only in the middle. So that's from negative square root of 5 to square root of 5. And it's concave down from negative infinity to negative square root of 5 and square root of 5 to infinity. And then they want those points. So we've got to plug it back in. And I'm about to run out of recording time here, but you would just plug square root of 5 in here. So you get square root of 5 plus 3 times the natural log of 10 for 1. And then negative square root of 5 plus 3 times the natural log of 10. Just plugging that back in. All right, a lot of work in those problems, but that is how to find the extrema and the inflection points of a transcendental function.